All right, so now I've started recording. So today we're moving on to force of friction. So this is quite an important force. You will deal with this heavily with dynamics from now on. And in next year when we do dynamics, everything's got friction. So let's get into this. So there's your SpongeBob and Patrick. So we've got friction is created whenever you've got two surfaces that are rubbing up against each other. So if you're nervous and you tend to rub your hands together like this, you create some friction. You try and push something across the floor, there's friction. You drive a car, there's friction. You walk, there's friction. Basically, anytime you've got two surfaces rubbing against each other, you get some friction. So this should be on the friction sheet. There's a box to fill this in. And where this comes from is if you look microscopically, so you zoom in really close, there's irregularities on the surface. So not everything is completely smooth. So even the desk, what you have, if something looks smooth, it isn't necessarily smooth. So your glasses, stuff like that, it might look from your perspective that it's smooth, but it's not. What it actually looks like is maybe something like this. So if we zoom in here on the tires, here's the tire, here's the road. There's bumps. So these bumps are going to rub against each other and cause friction.
Why did it seem like rubber and stuff have more friction?
Because they have more bumps, more ridges. So think about your fingers, right? Your fingers are pretty grippy. Why do you think that is? Your fingerprints, right? You've got a whole bunch of ridges on your fingers that you can actually see, and that causes them to be quite grippy. We'll get to that. It does depend on some of those things. So I think, I forget if on there's a little box where you can draw this. I don't remember. So this is essentially what friction is. And lots of what we're going to be dealing with, as you've seen last section with forces, with doing free body diagrams, drawing friction, it's all because you've got boxes moving on surfaces or whatnot. This PowerPoint is up on Google Classroom, so if I ever go too fast or you don't write something down, you'll be able to go back to it later. So this is your equation for force of friction. So F with a sub F to mean this is a force, but it's the friction force, equals mu. So this is like a U, but it has a little trunk in the front, times Fn. So mu is a Greek letter. Let me write out like this. Okay, so normal force. Fn is the normal force. We've talked about normal force before. We did that when we talked about forces. So normal force is the force that's perpendicular to your surface. So depending on what your surface is, that can change directions. So for instance, suppose this is my surface. I've got a normal force that's pointing up like this, if I put something down on it. If I tilt it, my force changes as I tilt this. So it's always at 90 degrees, no matter what. Till I get to here maybe. If I flip it upside down, now it's on the other side, so it looks a little bit different. But it's always 90 degrees. So everything that we deal with in this year, Physics 11, it's always going to be at 90 degrees. And your normal force is most of the time going to point up.
What if it's like the surface is 90 degrees?
Well, we'll get to a question that looks like that. But in general, you're going to have things that sit on the surface, normal force is up. Next year I change all that, and we get into some inclines. But for now, it's mostly just going to be up. And as I said, always perpendicular to the surface. That's what you need to remember for it. So mu This is our coefficient of friction. So for this, there is no units, so you don't need to remember the units for this. As I said, it's a Greek letter. And this value depends on both surfaces. So depending on what two objects you have that are in contact, it's a different value. So I'm sure somewhere out there is a giant book that has a list of all the different things that you could have in contact, and it gives you the mu. So someone's gone out and they've been like, okay, let's calculate between birch wood and cedar wood. Rub those together, what's the mu? Let's do steel on ice. What's the mu? Steel on steel, ice on ice. Someone has thought of all these different combinations and has calculated those. Basically, yeah. It sounds like a boring job. I wouldn't want to do it. But for our purposes, on the back of your formula sheet, I list 1, 2, 3, 4, 5, 6, 7. So there's 7 that I put on here. So either I will give you something is wood on wood, or ice on ice, or steel on ice. I will tell you those from here, or I give them to you in the question, or you have to calculate it. So either I give it to you, or you need to calculate it. Yes, that's like next slide or 2 slides. Yes, there's a difference in that. So mu just only depends on the two surfaces. It doesn't matter how big the two surfaces are. It doesn't matter how heavy of an object there is. It only depends on the two surfaces. We're going to get to that next slide. Or next 2 slides, something like that. Any questions on this? What's what? N? Force of friction. So there's 2 types of friction. We've got our static friction and we've got our kinetic friction. So static friction means exactly what static is. If something is static, it's not moving. So static friction is the friction force that occurs when you're trying to overcome an object sitting still. So everything on my desk, static friction. It's not moving, so therefore it is static. If I want to get an object to move by applying a force on it, I need to overcome this static friction. This is in contrast to our kinetic friction, which, as we did last unit, kinematics, motion. So kinetic friction is friction force on an object that is moving. So this is the difference. So on the formula sheet, it says mu S, mu K, static, kinetic. So these two are different. Oh, it doesn't say S or K, it just says static, kinetic. Yeah, so it has the S or K there. So the question is this: which one of these two do you think is going to be larger? So if I've got an object, do you think that its static friction is bigger or its kinetic friction is bigger? Okay, anyone who said static, why do you think static friction is bigger?
Because it has to be overcome first, and then to be able to move forward. The kinetic friction is already moving.
Okay, so you're saying because you have to overcome something being still, then you need a bigger force? Okay. Kinetic friction, someone who said kinetic, why do you think that that one is bigger?
Because, for example, the force that holds a car that is turning, that's like the force of friction on the ground that's probably bigger than the car is just standing still.
Okay, so you're saying if a car turns around a corner, it's going to be like a greater friction force than just one that's standing still? Okay, so those are both good arguments. However, the static one is generally bigger, or not generally, sorry. The static friction is usually bigger than your kinetic friction. Where this actually comes from, and Zena was kind of hinting at this a little bit, is if you are overcoming something because it's sitting at rest, what are we dealing with in that case if we're thinking about Newton's laws? What does Newton's first law say? Some with an unbalanced force, yeah. An object at rest wants to do what? It wants to stay at rest. But an object in motion wants to stay in motion. Unless you have an unbalanced force, yeah. So if something's at rest, meaning it has static friction, I need to apply a lot more force to get it started moving, as opposed to something that's already moving. So this is really just Newton's first law packaged into friction. That's essentially where that comes from. You don't have to memorize this, because conveniently it's on your formula sheet. Just take a look at which mu is bigger, and you can tell which one should be bigger from there. Good with this?
Is it bigger by a certain amount?
There's not a specific ratio that it changes by. It's just this one's bigger. Off the top of my head, I can't think of a case where these are equal or kinetic is bigger off the top of my head. Because most cases you're going to deal with static is bigger.
What about like friction?
So it's still in motion. You're still going to have a lesser kinetic friction as opposed to if it's standing still. Because it wants to tend to continue to move, right? So that's why there's less resistance to it. All right, so I got 3 examples. So we've got a block. It's being pushed on a tabletop with this force, and you're given the coefficient of friction. We want to find 2 things. We want what's the force of friction and what's the acceleration. So first of all, let's figure out what we're given in the question here. When in doubt, that's a good place to start. So what is this? Easy one there. What is this? No, not a normal force. Nope, not the weight. It is pushed along a tabletop with this force. This is your force applied. The coefficient of friction is this. So that just even tells you that's mu. So now let's figure out friction force. So there's 2 ways I can go about solving friction force. Either force of friction is mu Fn, so the equation at the beginning of the notes, or net equation. F net equals force applied minus force of friction. Which do you think we're going to use in this case? F net? So F net would be this minus force of friction. I don't have acceleration yet. So I can't actually figure out what F net is. So I'm just going to use force of friction is mu Fn. Do I know what Fn is? Is it given to us in the question? No. How could I get Fn? Is it the same as the force of gravity? What do you think? Yeah. So if I were to draw a free body diagram, here's Fg, here's Fn. We're not told any directions, so let's just assume force applied is this way. Force of friction is this way. So because it's on the surface and it's not accelerating up or down, Fg must be equal to Fn. So now this equation just equals mu Fg. What does Fg equal? Mass times the acceleration due to gravity. Because we're on the surface of the Earth, let's just assume g is 9.8. You don't need to do this as capital G, capital M times m over r squared, because we're on the surface of the Earth. So this is just mu mg. Now we have all these numbers. We can calculate this. We have mu, 0.65. We've got m is 3.75. And capital G. So let me move this a little bit over here so I can write this. And let's calculate this. So do this, we get the friction force is 23.9. I'm going to round it to 1 decimal place. Any questions with this? Yeah. If it's not on the surface, you wouldn't have an Fn, and then things would get more complicated. So typically with friction questions, it's always going to be the normal force equals Fg if something's on a flat surface. Again, next year I'm going to mess up that statement, but for this year, if it's on a surface, Fn is going to equal Fg. When in doubt, draw the free body diagram, because I will always tell you.
If it's not on the surface, is it air resistance?
It might be air resistance, it might be some sort of lift force, it might be tension. There's a bunch of things it could be. All right, so this was A. I didn't write that. This is solving for A. Now let's solve for B. So with B, we're going to use the F-net equation. Typically, if you want acceleration, either it's kinematics, which we're given nothing for this, or F-net equation. So in this case, F-net is equal to which force minus which force? What's my bigger force in this case? Thanks, Adam. I appreciate it. Almost everyone except Adam solved that one. So, so we said force applied is bigger. All right, this time Adam. Why do I know force applied is bigger in this case? You're not Adam. So why am I doing force applied minus the force of friction this way? You're not Adam. You don't want to answer that one? All right, Mahmoud, why? Exactly. So force applied is bigger, so I go bigger force minus smaller force. Or, as I said previous unit, winners minus losers. So this force is bigger, so therefore it needs to be minus that one. So we got MA equals force applied. We know what that value is. Minus, I already solved for force of friction. So let's just leave that there. And now I can get acceleration. Mass is 3.75 times A equals force applied, which we said is 45, minus 23.9. So subtract, then divide, and we get with this 45 minus 23.9 divided by 3.75. So we get 5.63. Do I need to give direction in this answer? No. Why? Yeah, we have no direction given here, so our answer does not need direction. It's literacy week on the elementary side, so they do this to say drop everything and start reading. That's essentially what they're doing. It's not a fire alarm, although sometimes that is the fire alarm. Although I wouldn't mind having a drop and a read. If just as a minor plug for this, if any of you like reading fantasy books, I'm in the middle of reading a series right now that is the best series I've ever read. If the only challenge is it's over 1,000 pages every book. So, but if you want to, it's well worth it. His name is Brandon Sanderson, so maybe it's just because he has the same name as me, that's why I like it. But he's also really good at writing. Any questions with this? No? Easy? I hope it's easy. But just wait. That was only the first question. Okay, so we've got a hockey puck that is pushed along the sheet of ice. We're given a force. We're told it's moving at a constant velocity. Find the coefficient of friction. So again, let's talk about some strategy with this. If you are ever lost on a question, which might happen, will probably happen at some point, what do you think is a good place to start? Even before that. But that is a good place to start. Free body diagram is great, but even before we do that. Reading the question, yeah, that's a good start. What do you do right after you read it, or even as you read it? Underline what's important. Because I can give you lots of dummy information in here that you don't need to use. But if we highlight it, name already what some variables are, you're good. So what's something important you can pull out of this question? Yeah? All right, so we got a mass.
The friction, the 0.240.
Is this the friction?
The applied force.
Yeah, this one's applied. What else? Someone else hasn't said something yet. Okay, what does constant velocity tell you? Yeah, what else? Yeah, the speed doesn't change, but what does that tell you? Acceleration is 0. And why does knowing that acceleration equals 0 help us in this question? Yeah, so this is saying all my forces together add up to 0. My forces are balanced. What else are we given in this question?
What to find?
Mm-hmm. And what are we looking for?
The coefficient of friction.
So this, is that all? Yeah. So this is a great place to start. Because instead of just having a bunch of words, now you've got some variables that you know. So this will help you in moving forward. We want the coefficient of friction. We're looking for mu. So not force of friction, what's the mu value? All right, so we also said drawing a free body diagram is helpful. So let's do that. Often I give you marks for a free body diagram if you show it. So it's well worth doing. So what are some forces we got here? All right, so I got a normal force going up. Force of gravity going down. Yeah, we know these are the same. All right, so we got a force applied. Just to mess with you, let's do force applied in this direction. Really doesn't matter. Force applied, what else? And a friction force. So which one's bigger, force applied or force of friction? They're the same. Remember we said F net is 0, so this force has to equal this force. All right, so what do we do next? Let's see. So if I want to solve for coefficient of friction, I'm going to need to use the friction force. That might be helpful. And how can we do that? Well, let's write it out. So I've got force of friction equals mu Fn. Do I know what my force of friction is?
Yeah.
I do. It wasn't given in the question, but how do you know what this is? They're the same. So force of friction is equal to force applied. That variable we know. Do I have the mu value? Nope, that's what we're looking for. Do I know what Fn is? Yeah, so it's the force of gravity. So notice I'm just substituting in variables that I know. Because Fn, we don't know. But we do know what Fg is. That one we can calculate. So now let's plug in numbers. Force applied is 0.24 equals mu. Fg, so this is equal to m times g. So 0.2. Again, we're on the surface of the Earth, or we're not told otherwise, so we're going to assume that. Now we can solve for mu. 0.24 divided by 0.2 divided by 9.8. And we get a mu value of 0.122. And what are the units for mu? No units. How's that possible? Will it be newtons? It is no units. But how come? Coefficient doesn't automatically tell you it's unitless. If I take this equation and I rearrange it, what does it equal? They're not. Yeah, so force of friction divided by force normal. So if I wanted to solve for mu, I just divide Fn onto this side. What's the unit of force of friction? Newtons. What's the unit of force normal? Newtons. So newtons divided by newtons cancel out. So that's where it comes from. It's not necessarily important, but that's just... You need to remember that. By doing all your practice problems, hopefully by that point you'll remember when to put a unit and when not to. Just like when do you know when to put direction and when not to. Lots of practice. All right, so this is my final answer. Questions with this? Good. I mean, not that if you have a question that's bad. Yeah. I'd rather you ask questions than not. Okay, now for this one. We've got a textbook being held against a vertical wall with a force of 45 newtons. What is the coefficient of friction between the book and the wall? So we've adopted a strategy with this, and let's keep moving on with that. So let's pull out information that we're given in the question. So we've got a mass. It's kilograms, so obviously that's mass. We've got a force. We're told it's held with this force, so let's just call this a force applied. And we want mu. Nope, not 0, sorry. Question mark. Anything else we're told in the question? Gravity isn't something. There's something else we know with this. With just this bit of information, we can't solve anything. Yeah, so it's going to be on the wall. What else could you tell me? It's not moving. How did you know that? Yeah, so it's not. It doesn't say it's moving up. It's not going down. It's not going whatever into the surface, out of the surface. It's held against a vertical wall. So if something is being held and it's not moving, what does that tell you? Acceleration 0. And if acceleration is 0, what else? F net is 0. So this tells me two things. Acceleration equals 0, F net equals 0. I make a big point of stating this because this is very important. This will save you a lot of hassle if you can recognize these bits of information. So it's very good for you to start off a question and figure out what's given here. Next thing, free body diagram. So I'm going to draw the wall here. Typically you don't, but I just draw the wall for reference so you can see what's going on. What are the forces that are acting on this object? Let's start with an easy one. Where is force of gravity? Down. Where is my force applied? It's pushing into the wall, right? I've never seen anyone hold a textbook against a wall any other way. Where is my normal force? Remember the definition of normal force is it's perpendicular to the surface, 90 degrees from the surface. So it's going out from the wall. Yeah, thank you, Adam. So remember I said force normal isn't always upwards, just in general it is. What about friction? Against the wall to the left? Well, let's think about this. If there's no friction, what's going to happen to the book? It'll go down. So therefore friction has to oppose that, so it has to go up. Yes, but it's not saying you're sliding up the incline. It just says against the wall, it's held in place.
Then what is the force applied?
The equations will come in a sec. So I'm told everything's balanced, so I leave it like this. So suppose this is my textbook. If I'm holding this against the wall, right? So I'm applying a force into the wall. The wall's pushing back, so that's the normal force. Gravity pulls it down. Friction's what's causing it to go up. So that's what I've got in this case. So we can go about now calculating some of these things. We are looking for coefficient of friction. So again, let's do force of friction is equal to mu Fn. And let's start replacing some of these variables with things that we know. Force of friction, what is that equal to? Force of gravity, right? These two are opposed. So force of friction is equal to Fg. Mu is what we're looking for. What is the normal force equal to in this case? Force applied. So this kind of a question twists up where you think the forces are. This is why physics can be very confusing, because memorizing equations won't work. Because I can give you a situation that changes everything that you've seen before. So really, you need to remember strategies in this class, not just memorize equations. So the strategy, find the variables, free body diagram, make an equation from your free body diagram. So Fg, this is just mass times gravity. So 1.1 times 9.8. Mu is what we're looking for. We have force applied. So we can now solve this. We get mu is 0.2, I'm going to round this to 2.4. I'm not going to be super picky about rounding. I know in the answer keys for your worksheets, they often round the answers. As long as you give me like 2 or 3 decimal places, you're good. I'm not going to be super picky about that. Just don't give me like a huge long number. Like at least round it a little bit. Any questions with this? Does that make sense? Okay. So what you'll want to do now is work on the worksheets for this. I will give you the warning now. The lab that is coming up for you guys, which as group 1 is going to be on Sunday, the lab is all about friction. It's all about this stuff, yeah. So make sure it'll involve a little bit of some other stuff, but in general, friction. So just as a heads up, you really need to know this because what? The one that's written up on the schedule for on Sunday. Yeah, the schedule that I posted at the very beginning of the unit. All right, so I will stop it there.